You are listening to EE Times On Air, and this is EE Times Current. I'm Eric Singer. Today's episode is brought to you by Siemens EDA. Many IC design teams struggle with tight deadlines and limited resources. The industry is constantly searching for new ways to improve efficiency without compromising on design quality. And while they might find tools that run incrementally faster, the real gains come from advancements in the capability of the EDA tools that enable new design flow use models, including what we call shift-left strategies that pull sign-off quality verification into the design implementation stages. And it takes unique tool capabilities to tackle verification challenges that early in the process, but the results are game-changing. David Abercrombie is the Product Management Director for Artificial Intelligence and Licensing Applications for Calibre at Siemens EDA. David has driven the roadmap for developing new and enhanced EDA tools to solve the growing challenges in advanced physical verification, design for manufacturing, multi-patterning decomposition and checking, and artificial intelligence and machine learning. Prior to joining Siemens, David managed yield enhancement programs in semiconductor manufacturing at multiple companies. He's been extensively published in papers and patents on semiconductor processing, yield enhancement, and physical verification. David received his BSEE from Clemson University and his MSEE from North Carolina State University. Go Wolfpack. We'd like to welcome David to talk about how chip designers can use a shift-left strategy to boost productivity, speed up time to market, and improve design quality. David, thank you so much for joining us today.
Yes, great to talk to you today, Eric. How are you?
I'm doing great, man. I'm excited to talk about this topic. It's obviously a pressing concern for designers in the field. Shift left, we know, is nothing new, but applying it to Calibre is something that I think has been eagerly awaited. The idea of Calibre Clean being such a gold standard for designers. So, as we said, shift left is not a new term, and it's been used in many ways in lots of different application spaces. I'd wonder if you can give us an overview of what you mean by shift left in IC design and verification. And what were the motivations at Siemens for developing the shift-left philosophy within Siemens EDA's Calibre suite?
Sure, Eric. Yes, exactly. You're right. The concept of shift-left isn't new. In fact, the term was coined over 20 years ago, and the original use, I guess, of the term was around software development and this general concept of moving like QA tasks and stuff testing up in the software development cycle so you catch things earlier and you don't get way down in your development cycle before you realize you have a problem. So for Calibre, shift left is more than just doing things earlier in the design flow, running Calibre earlier. It's really also about revolutionizing the way you do it earlier. Okay, because designers, they've always done some level of verification all throughout the design stages. Although you think of it as a sign-off activity to say, oh, we can tape this thing out.
It's already too late.
Yeah, it's already too late. Or you hope at the end, okay, it's all clean. This is just saying everything's going to be okay. But obviously that's not practically true. And for a long time, people do various levels of verification as they go, so to speak. And you just think of Calibre as this final golden sign-off. Well, if it passes that at the end, we know we're good to go.
Right.
And so it's the issues we want to try to address are more about the quality of the verification you're doing in those earlier parts of the design flow and the productivity of the use model, okay, which I think is even maybe a bigger piece of it.
Yeah.
So when we set out to kind of create entirely new models for our industry-leading sign-off tool to optimize using it up in the flow where, in these other kind of unique scenarios. And the significance or the motivation or whatever is we really think it helps improve productivity for the designer, not only because we think these unique use models are in themselves more productive use models of doing verification, but by using the same golden sign-off engine, so to speak, throughout the whole flow, you don't end up with these surprises where, at the end when we finally ran caliber, we see there's a disconnect between the engines I'm using at different places, and hence it didn't catch something earlier. And that sounds like a traditional kind of shift left. We didn't find it out till the end. But there is a whole lot more to it than just doing it sooner.
Yeah, and especially when we think about caliber being that gold standard of verification, and to be able to know if it's caliber clean sooner in the process and to catch that in time to actually make changes before it's too late is huge. How do you see verification as part of the larger overall design process, and what kinds of complexity does the process entail in the real world?
Yes, typically because it's easier to draw on a slide, people depict the design flow as this linear set of operations that occur. One stage gets done, it goes to the next stage, it goes to the next stage until you're done. And that's never really been the case, and
it's a nice
particularly
dream.
Today. It's a nice dream. It's making it easy for a textbook for somebody to learn, but especially design today, trying to do it in a linear flow like that would never be competitive. You couldn't compete in the market today like that. And if you think of something like an SoC, for instance, you're integrating so many different separate pieces of IP blocks, memories, IOs, etc., to make up this final big chip thing that you're doing and all. And really, each of those pieces that make up this larger thing you're designing are on their own independent timelines with other people doing them. Like you said, it's not one person doing it all. It could be even different companies, much less different people in the same company doing different portions of this thing that are going to be tied together in the end. I mean, you're verifying the individual pieces, you're verifying the integrated piece, and they're all iterating, because you can imagine you make some change at a lower cell that might affect the pin location or something. And then that affects the routing at the top that the SoC person's trying to hook up to these things. Or the SoC person's making a change in deciding how to distribute the power or the clock trees across the pieces of IP. And that impacts a constraint for the lower level piece of IP.
Right.
It sounds like a mess, and a lot of times it really is.
But it's never been more true than today, when expectations are that we deliver products faster to market than ever before.
Yeah.
And at the same time, you've got this compounding problem of development happening so quickly on the various components that need for testing to happen in real time during all these stages. It's never been more critical.
Yeah.
I would imagine that the kinds of problems being found, and just as importantly, the process for fixing them in all those various stages and with all those various parties involved, can be quite different, yeah?
Yeah, absolutely. I mean, just kind of imagine in your head, you got some analog designer or memory block designer. They're probably working in a custom layout editor, and they're moving around single polygons and edges. And as they're early in their design process, they're just trying to get all the transistors in place and connected up to match the circuit to just get this thing doing what it's supposed to do. And in during that stage, they're just trying to verify that they're adhering to basics like spacing and width checks. I just fundamentally kind of doing the basics. And maybe they're sanity checking their pin connectivity and up to the upper level SoC. But as it matures, then they can start addressing the more complex constraints and verification, multi-patterning, density constraints, things that don't even matter till you got those basics done.
Yeah.
And if you're larger, like a standard cell block designer, you're probably working in a whole different tool, P&R tool instead of a custom layout tool, and you're focused on just getting all your cell placements in place and trying to get a basic route going initially. And again, you don't start worrying about higher order constraints like antenna checks that.
When you thought about that.
Yeah, you thought about that yet. That comes later in your design cycle. And then if you're the SoC guy at the top, you might be in either a custom tool or a P&R tool or both at times, depending on the methodology you might use for kind of putting things together and connecting them up. And again, you're initially first just trying to get all the IP placed, arranged, basic wiring them up, and getting your power rails and stuff. And so again, basic checks. You don't worry about things like delta voltage or your ESD latch up things on your IOs until you're much more mature in getting the thing together. So, and all of these people are doing all kinds of iterations of DRC, LVS, PERC, DFM, all kinds of checks and all kinds of categories. And like I say, focus on different portions of those checks at different times. And it's so much variety and so much difference with each designer and in each stage of their particular portion of the design.
Yeah, so just a ridiculous number of variables that are changing all the time.
Yes, it's a complex thing these days.
So we've talked sort of about the landscape of the current state of affairs. Can we drill down and talk about some specifics? What unique problems might occur in a specific scenario? What's an example of a shift left solution for that kind of use model? And how does it make a difference in the real world, everyday experience of a designer?
Yeah, this is where the rubber meets the road, right? Maybe let's take an example of like the initial DRC runs early on when, say, the SoC designer is first integrating the chip with the various IP blocks and stuff in the earlier stages. So imagine that stage is getting these pieces of IP from all these different sources, and each of those early on, they are very dirty. I mean, they aren't clean, they aren't fully formed and everything. They, in some cases, are just empty blocks with pins on them. So he wants to start verifying the basic checks on those things. But if you just were to say, oh, well, let's take Calibre sign-off deck and let's run it. Okay. Uh-oh. I mean, you're going to get hundreds of millions, we see billions of errors on runs like that. Okay. And you can imagine going, oh my goodness, where do I start? Yeah. It's overwhelming. And not only that, SoC guys knows that the bulk of those errors don't even belong to him. They're down in the pieces of IP he's pulling together and all these kinds of things. And so he can't even see what he's supposed to focus on because he's overwhelmed by all this issue. And you're running the full deck, then you're running all these complicated checks like multi-patterning, antennas, delta voltage density, of which you don't even care about. I mean, you haven't fixed the basics.
Yeah, so far down the road.
Right. So we developed this new shift left solution called Calibre NMDRC Recon. Recon stands for reconnaissance. So kind of get that idea in your mind, right?
Getting out in front of it.
Yeah, okay. So there's intelligence built in the tool that it analyzes all the checks that you have, and it figures out of all those kind of checks, which are those complicated checks and those checks that kind of are these more back-end things that matter later, or even some of the more basic checks, which ones are very complicated versus very simple, and it automatically turns those off and runs only the set of checks that says, in this kind of application, this is all you really need to focus on. These are the things you should start with. And you don't have to figure that out yourself or create manually specific check groups to decide to turn on or what on and which ones should you have in or not out. It just does it automatically. And what you'll see right off the bat is that the run will happen 60 to 80% faster. So right off the bat, you've saved just time, doing the run. Okay. And of course, you won't have errors from all those checks you shouldn't even be looking at anyway. So you're going to reduce 60 to 80% of all those billions of results to look through. But we don't stop there. I mean, it's so not even just ignoring we'll call them nonsensical checks at this point. You're still going to have results on the basic checks that are not the responsibility of the SoC designer. They're down in the IP or whatever, right? And that noise still hides what they want to focus on. So we have another shift left solution called Calibre Auto Waivers Gray Box that kind of goes the next step. Instead of Recon's focused on which checks to run, this is focused on which part of the layout to verify. Okay, and so it automates the deselection or whatever, or like blocks the SoC designer doesn't want to look at or whatever, and just does the error checking on the top level design and the interactions with the IP. And designers have tried to mimic this manually in the past by like putting a marker layer over the IP, so I just ignore this region. But the problem with that is you block out every error in that region. Okay,
Right.
so not only what's down in the cell, but all the interactions that are occurring between the upper level routing and the cell and the pins and everything. So this is a much more automated, intelligent solution that still shows you those, because the SoC designer cares about the interactions with the IP and to the pins and all that kind of stuff, and just wants to hide the noise, so to speak, of what's underneath. And so and that will reduce the runtime an additional 50%. From not running useless checks, not running useless regions, areas, and things, you now get massive runtime improvement and massive reduction in the errors, and you're kind of left with the errors that really matter for now.
Yeah. I mean, as you're talking about that, I'm imagining the old analogy of looking for a needle in a haystack, right? And in
Exactly.
this case, there's multiple needles in that haystack.
Yeah, there's multiple needles in a haystack, and it's a big haystack, right? And then the next solution that kind of takes it to the next level. Now that you're down to the ones that matter, okay, now I'm where I need to look at. We have another shift left solution called Calibre Real Time. And so this actually lets Calibre run inside the tool you're using to do the design, if the P&R tool or the custom editor, whichever one you have, and we're independent of vendor, we don't care which one you use or anything. It runs in all the normal everybody's tools. And so you can actually run the Calibre engine in real time within the tool you're in, okay, as you're making changes. So now you're looking at results. You say, oh, I got an error here. And you decide, I'm going to move this to see if that fixes it. Calibre runs instantaneously in that region and tells you, did you fix it or did you cause a new error?
Wow.
So you're getting like this real time, as you move things, feedback while you're doing the fixing part, right? So it's not like because otherwise you'd spend 4 hours making what you think are fixes, right? Mm-hmm. And then you do another batch run that takes hours to run, and come back and find, oh, I created a bunch of new errors. I didn't fix half of them. So you see the productivity improvement?
Absolutely. Well, I mean, think about like placing the marker layers, using that approach. Okay, you're still looking for needles in a haystack, and now maybe you've taken a section of that haystack and you've moved it to the side, but you got some needles in there that you're looking for. You're missing them. And this real-time approach actually lets you figure out where in the haystack are the needles that you care about and finds those for you.
And helps you.
That's a heck of a lot less hay to sort through.
Oh, absolutely. And much more productivity while you're doing the actual fixing part of the flow. So you see how when we say shift left, it's not just running Calibre sooner. It's running it in completely new ways so that it's much more appropriate or productive for the particular use model, you see?
When you talk to folks who are using these tools out in the field, in the real world, what kind of feedback are you getting from those people?
Oh, absolutely. Yeah, we're getting tons of great feedback as people learn to use them, and it's kind of funny to see people like, whoa, I never thought of that kind of thing. And when they finally kind of clicks what it is we're trying to do, they start to see, whoa, this really helps. And
right, there's all kinds of other possibilities, that show up. Not just how do I get rid of the errors, but
how can I be more efficient? Yeah, we can do this. Yeah. Google, for example, they use one of our shift left tools called Design Enhancer, and it's an interesting example of using the Calibre engine, so to speak, that has been so good in the industry to perform something totally different than it's usually been thought of doing, and this is design optimization. So this Design Enhancer tool has 3 use models that augment or kind of replace stuff you've done in place and route chip finishing historically. Okay, and these are like redundant V insertions, redundant and ground metal and V insertion to help with resistivity in your power and ground rails, and then your decap and filler cell insertion. So these are things that people have done for a long time, but they've used P&R tools to do them, and this is a Calibre engine alternative to that. And at Design Automation Conference this year, Google presented their results of using it to improve their power grid IR drop. And they let Design Enhancer try to maximize these V insertions and power net changes and stuff. And then they measured insertion rates and run times and stuff. And it turns out because Calibre uniquely understands all the design rules, because that's what it does. You think of it as a verification tool, right? So it understands the design rules. When we use it to do things like inserting vias and all, it can do them, understands the layout very well, and turns out it can do a very good job at it, and it does it caliber clean as it's doing it, okay? So what they saw is the via counts improved 43% over the P&R method of doing it. On one block, and 82% on another block better than the P&R. So that's a better result just in count of how many it was doing. Yeah. For the runtime, okay, the traditional P&R method took about 6 hours on one block and 8 hours on another block. But with the design enhancer flow, they did it in 20 minutes and 40 minutes respectively.
Wow.
So 6 to 8x improvement in just sheer runtime of doing it. But the key is all this is about addressing IR drop, and in the first block it reduced it by 94%, and on the second block by 90%. So they got these great results, and from a shift left kind of thinking process, this is why I think it's very different kind of way we look at it, is this is in a way moving caliber upstream, but doing something even it never did before, like you would think of another kind of tool doing, okay? That who thought a verification tool would be optimizing layouts, not just checking them. But it turns out being good at checking them makes you pretty good at tweaking them too. And as you tweak, you inherently can measure whether they're clean. So you don't have this problem of not only did it do a better job, but you can imagine, okay, I used the P&R tool to do it, and okay, it did enhance the layout, but then I run Caliber and find out, but it broke a bunch of rules. And now I got to go back and redo half of them. So you see the productivity gain. And
I mean, just thinking about the runtime thing alone, it's like, okay, you're talking about days and days of downtime, and all those things, of course, always have this domino effect where the ramifications of each one of those delays are delaying other things from happening.
Especially when you think about those overlapping cycles of all those different things being designed. If each of the individual pieces is slipping, then the overall thing is going to slip.
Yeah, and pretty soon you're looking at this exponential curve of delay, and you're not getting to market in time, especially with the expectations these days. So with your knowledge and background in AI and machine learning, I know you're very tuned into what is trending, what's ready for prime time now, what tools are coming. Where do you see shift left going in the next few years? Are there emerging technologies or design needs that you think are going to further shape shift left verification?
Oh yeah, absolutely. And that's a good question. I kind of like playing Nostradamus, but yeah, it really is kind of the tip of the iceberg. I mean, really, in a lot of ways, only getting started thinking outside the box. I mean, it's funny how you start thinking outside the traditional box, and it kind of opens your mind, right, to the various things that we could potentially do. I mean, for instance, we're building solutions right now that help manage and optimize the verification of 3D ICs, because now it's not just one chip you're making, right? You're making a whole 3D IC of many chips combined together. So how do you verify
Speaking of exponential.
Yeah, it's not just the individual ones, but them together and all that kind of stuff. It's a massive problem. It's very difficult. And so we're building solutions for that. There's new technologies coming like multi-gon support for things like silicon photonics. So silicon photonics are the shapes aren't rectangular anymore, aren't Manhattan. You got curves, okay, in a layout. That's a weird thing. And we've always represented those as piecewise linear little snapped grid things. And that's in the future, that's not going to be sufficient. We have to treat the curve as a true multigon is a term for that, for capturing the true curvedness of the thing. And how do you verify a curve, okay? And we're getting into the multi-physics space, so analysis, verification of things like power, stress, temperature, so not just design rules and things like that, or electrical things, but all these other multi-physics things that all interact, and if the power goes up, the temperature goes up, the stress goes up, they all interact with each other, all these things. So there's all kinds of new solution development going in terms of like new tools, new fundamental technology. And then as you mentioned, on top of all that, you got machine learning and AI, which is more of a general toolkit. So there's tons of activity going on in that space.
So you've talked a lot about all these great opportunities that are available right now for designers and what is coming next for improving the productivity of designers and the quality of the output. Where can we direct listeners to go to find out more about all this?
Okay, yeah, sure. The easiest way is probably just go to the Siemens.com website and have all kind of information about the tools, resources like technical papers, videos, fact sheets. Just go there and search for Caliber Shift Left, and you'll get to the Shift Left homepage, and you can see a bunch of stuff there. And of course, our customers have direct access to our support people that work with them every day, the account managers and AEs and stuff, that they can, hey, I heard about this Shift Left stuff, tell me more. And we'd be glad to give them more detail as well. And for me, I just hope that it goes beyond a concept and a tool. And I just like seeing an engineer going, wow, you just saved me a week of headache.
Yeah.
There's nothing better than just see the relief of somebody actually tapping into the power of some of these things and just taking a weight off their shoulder in a way and making them more productive, because they feel a lot of stress. I mean,
absolutely. There's so much pressure on designers these days.
They really are. In some ways, they're the victim at the bottom of all this, and we just hope that, that these things ultimately can help them out and make their lives a little bit better every day.
Absolutely. Man, this is really exciting stuff. I am so grateful to you for coming on the show and sharing your insights about Caliber and Shift Left. We'll include a link to the areas on the Siemens website where folks can go to learn more about this. Thank you so much again for taking the time to talk with us today.
Absolutely. I'm always excited to talk about it. It really gets me going too.
That brings another episode of EE Times Current to its end. Thank you for joining us today, and thank you again to our guest, David Abercrombie from Siemens EDA. EE Times Current is available through the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. EE Times Current is produced by EE Times. It was engineered by Taylor Marvin at Coop Studios. I'm Eric Singer. Thanks for listening.